For the first part in this video, I will explain the introduction, which consists of few definition of things that we further explain in this video soon. First of all, it is important to know what is function. So a function is a numerical relationship where every input has exactly one output. We can also say for every x there is only one y. So the symbol of function is f of x, and there is a way to tell if something is a function which by vertical line test. Vertical line test is a graph represent a function if there are no vertical line that intersect the graph at more than one point. So as I said earlier, for every x there is only one y, means function should never cross the vertical line twice. So let's look at the first example. It crossed 2 times, which means they are not function, and for the second example, no matter where the lines draw, it only crossed them once, so it is a function.
Today I will talk about 5 types of transformation, which is vertical shift, horizontal shift, vertical stretching or shrinking, horizontal stretching and shrinking, and reflection of graph. Next is the formula that can be used in this topic. Number 1, vertical shift. As you can see, vertical shift, the C is placed outside the function. In the meantime, for horizontal shift, the C is placed inside the function. Next, for vertical stretching or shrinking and horizontal stretching and shrinking, you can see the position of C is different between them. C is placed on the outside for vertical, and in the horizontal, they place the C inside the function. Next is formula for reflection of graph. To make it easier, when you see negative on the outside, it reflects on the x-axis, and if it has the negative on the inside, it reflects on the y-axis. In the next slide, I will explain further more about the vertical shift. If C is positive, shift graph upward. If C is negative, then shift graph downward. Use the parent graph to obtain new graph. You can shift the graph by C point. For instance, function x equal to x power of 2 plus 3. As you can see, the C is outside the function and in positive. If C is positive, then we can move the graph upward by C point. In this case, is 3. Next is the horizontal shift. In horizontal shift, if C is positive, then move graph to the left. And when C is negative, move graph to the right. Graph shift by C point. The third one is vertical shrinking or stretching. The graph will vertically stretch when C is more than 1 and shrink when C is less than 1 and more than 0. To transform it, multiply the y coordinate by C to get the new point. For instance, function of x is x power of 3. If the constant is 2, then multiply 2 with y coordinate. When stretching happens, graph will be narrower than the parent graph. Meanwhile, when the graph shrinks, the graph will be wider than the parent graph. Number 4 is horizontal shrinking or stretching. First thing first, we need to identify the constant value. Either C is more than 1 or C is less than 1 but more than 0. Then get the x coordinate by constant to get the new point. For instance, function x equal to 2x power of 3. Then 2 equal to C. Multiply 2 with y coordinate. On the picture shown in this video, the picture on the left is shrinking, meanwhile the right picture is stretching. Last but not least is reflection of graph. Reflection is when the function is negative, either it's on the inside or the outside of the function. When the negative is on the outside, multiply x, then the graph will reflect over x-axis, and when the negative is on the inside, you will multiply y, and the graph will reflect over y-axis. For instance, function of x equal to negative x power of 2, then multiply negative 1 with x.
Based on the picture in this video, you can see that the graph is reflect over x-axis.
Let us look at some of the examples when transforming graphs of function. Let's start with a function. In this case, it is f of x equals to x squared. By adding a constant to the y value, the graph will move 3 units higher. If it is a negative number, the graph will move downwards because these are called vertical shift. When there is a constant to the x value, the graph can move to the left or to the right. However, this one might be a little tricky because it is kind of opposite direction. Always remember that a positive number will move the graph to the left, while a negative number will move the graph to the right. These are called horizontal shifts. For this example, we know that the function has vertical shift of 1 and horizontal shift of 2. So negative 1 move the graph 1 unit down and positive 2 move the graph 2 units to the left. And these are combination of vertical and horizontal shift. This one shows that a graph can stretch or shrink by multiplying a constant to the whole function. In this case, it is greater than 1, so it has been stretched out and twice as narrow. If the value less than 1, for example 1/2, the graph will compress in opposite direction and becomes twice as wide than the original because it grows at half the rate. These are called vertical stretch. If there is a constant multiplied by x, for example 2x quantity square, the graph will shrink horizontally. If we replace with 1/2, then it will stretch up horizontally. As you can see, this horizontal stretch affects the graph differently compared to the vertical stretch. We need to always remember that if the value is greater than 1, it will shrink, and if the value is less than 1, it will stretch. It is kind of opposite to the vertical stretch, where bigger value cause more stretch and value less than 1 cause the graph to shrink. Next is example of graph reflection. For instance, f of x equals to negative x squared. If we multiply the whole function by negative 1 or negative, the graph will flip upside down or reflected across the x-axis. However, if we multiply the x value by negative 1 or negative, the graph will flip left-right or reflected across the y-axis, but cannot be seen in this example because x squared is symmetrical about the y-axis. So here is another example which is done on square root of x. As you can see, the graph reflected across the y-axis because we multiply x by negative. Another one example with x cubed function that also reflected left-right or crossing the y-axis. All this kind of transformation can be applied to any type of function. Lastly, let's have a look at the function or example here, where we need to apply several combination of transformation. Given f of x equals to negative 2 times x plus 3 quantity squared minus 2. Then do one by one starting with x squared. Firstly, notice the constant to the y value, which is negative 2. It shows that it is a vertical shift. So the graph will move down by 2 units. Next, the addition to the x value indicates that it is a horizontal shift, but also remember that plus 3 is actually means the graph is gonna move to the left by 3 units. After that, the multiplication of number 2 here to the whole function shows that it is a vertical stretch. Since the value is greater than 1, the graph will stretch out by a factor of 2. And lastly, the negative sign multiplied to the whole function means the graph will reflect upside down or reflecting across x-axis.
When do we use function transformation? Why in the world do we even have to know this stuff? Below is a list of where you will use function transformation in mathematics as well as some real-world example using function transformation. Function transformation in mathematics. Transformations are used to move geometry shapes around a coordinate plane in geometry class. Function transformation can be applied to be more complex equations such as logarithmic and trigonometric equations. Function transformation can be used to graph or find the formula for graphs that are not easily found otherwise. Function transformation in real life. Animation requires a figure to be shifted and stretched on a plane. Computer animation software use advanced transformation to achieve this. If functions are used to model data, a shift in the data can be reflected by a function transformation. So this is the example of animation that use the function transformation concept.
Hey, lady, take your infested patty with you. Okay, no need to panic, Squidward. It's just a puny urchin. Everything's gonna be fine as long as you...
For this part, I'm going to show some exercises and its solution. First, I'm going to show 6 objective questions and of transformation of graph and how to solve it quickly and correctly. Okay, this is the first question. The blue one is the original function and the green one is transform function. First, what we need to do first, we identify the type of transformation. As we can see, the original graph move to the right, so we can conclude that this is horizontal translation. Okay, as my friend explained in the previous video, for horizontal translation, the equation will be like this. So we will use this equation to solve this question. So at the answer, okay, we can conclude that A is the answer. Okay, this is the second question. Like I said before, first we need to identify the type of transformation. As we can see, the original function, the blue one, move upwards, and the green one is the transform function. So as my friend explained in this previous video, so this is vertical translation. Okay, for vertical translation, the equation will be like this. So we will use this equation because it translates up. Okay, we take 1 point. So I take this point. So we count how many times the point move. So 1, 2, and 3. So A will be 3. So the answer will be A. Is the third question. Okay, like before, first we identify the transformation. As we can see, the blue line is the original and the dotted line is the transformation graph. So as we can see, the graph horizontally shrink. So the graph shrink. So we use this equation, and as we can see, we take 1 point. Okay, 4. Then the transform equation, it becomes 2. So the answer, so 2, the value of C is 2. So for this question, the answer will be C. So this is the fifth question. Okay, the first step, always like always, we identify the type of transformation. Okay, the blue one, the solid one is the original graph, and the dotted line is the transform graph. So as we can see, the graph reflect on the x-axis and y-axis. So this is type of reflection. So for reflection, the formula or equation that we will use, like I said, this graph reflect x-axis and y-axis. So we have to combine this equation. So the answer will be like this. So this is G. So G, X, negative X, negative X. So the answer will be D. Okay. For the reflection, we use like mirror concept. First, as we can see, the transform graph inverted from the original one about x-axis. It will become like this. So you imagine the graph will be like this. Then about y-axis, so it will be like this. Okay, this is the last question. This is the graph of function f. Function g is defined as gx f negative x. What is the graph of g? So this formula is for reflection. Reflection of what? Like I said before, this is for reflection about y-axis. So we use the mirror concept for the reflection type of transformation of graph. So it will become like, imagine this is the mirror, then it will become like this. So as we can see, the answer will be C.
These parts of this video will summarize and give overall conclusion how the values of a, b, c, and d transform the function of f of x. First is the value of a. When y equal to a times f of x for a greater than 1, it will stretch the graph of f of x vertically by a factor of a. And when y equal to a times f of x for a between 0 and 1, it will compress the graph of f of x vertically by a factor of a. One way to find coordinates of a transform function is this form would be able to find point on the parent's function. Keep the x coordinates the same but multiply the y coordinates by a to find the y coordinates of the transform function. Let's take a look at the graph. So the red function is the parent function and the blue function will be the transform function. So when a is greater than 1, the blue function will be stretched vertically by a factor of a. And also notice that the x-intercept do not change when we stretch the graph vertically or when a is between 0 and 1. And the blue function is compressed vertically. Now let's talk about the value of b. When y equal to f of bx and b is greater than 1, this will compress the graph of f of x horizontally. And when y equal to f of bx and b is between 0 and 1, this will stretch the graph of f of x horizontally. So again, if we know point on the parent function, we can determine the coordinates of the transform function with different values of b by multiplying each x coordinates by 1 over b, or just divide by b and keeping the y coordinates the same. So we can say the transform function is stretched or compressed horizontally by a factor of 1 over b. So now let's take a look at the graph. So the transform function will be in blue and b is greater than 1. We will see that the transform function is compressed horizontally. Notice that the x-intercept do not change now, and if b is between 0 and 1, the function is stretched horizontally as we see here. I want to summarize of what happened when we change the sign of a and b. So let's first consider when a equal to negative 1. If x equal to negative f of x, this will reflect f of x about the x-axis. Remember f of x equal to y, so we will be changing the sign of the y coordinates. When b is less than 1 and specifically equal to negative 1, where y equal to f of negative x, this reflect the original function f of x about the y-axis. Let's take a look at the graph. So we decrease a, and as soon as a is negative, it will be reflected across the x-axis. And when a equal to negative 1, the blue function is a perfect reflection of the red function across the x-axis. And we also have vertically stretched when a is negative. And when b is equal to negative 1, as soon as b is negative, it will be reflected across the y-axis. And then when b is equal to negative 1, it's a perfect reflection of the original function across the y-axis. Now, we will see how c affect the graph. So if we have y equal to f of the quantity x plus c, this will shift f of x left c units. And if we have y equal to f of the quantity x minus c, this will shift the function right c unit. So let's take a look at the graph. So notice when we see x minus a constant, the blue function is shifted right c units. And if we see f of x plus a constant, the graph is shifted left unit. And lastly, we have the value of d. If we have y equal to f of x plus d, this will shift the function up d unit. And if we have y equal to f of x minus d, this will shift the function down the unit. And remember, for f of x equal to y, so this is adding and subtracting values to the y coordinates. So let's take a look at the graph. So if we have f of x plus d, the function is shifted up d units. And if we have f of x minus d, the function is shifted down the unit as we can see. And that's all to summarize for this unit. Thank you.